Everyone welcome Dr. Dongarra to the stage as our first keynote.
So I'd like to talk about high-performance computing. Sometimes it goes by the name of supercomputing. And for years, science was moved forward by theory and experimentation. So theory is a paper and pencil kind of thing where we put down some ideas. Experiments are where we take those you think about putting it into a cabinet. So we fill up a cabinet with these boards and connect things together using some interconnect. That may be gigabit Ethernet, it may be InfiniBand, it may be some proprietary mechanism that allows messages to be communicated very rapidly. And of course, we're not going to be satisfied with just one cabinet. What we'd like to do is to fill up a room with those cabinets. So at Oak Ridge National Lab, not too far from here, we have the fastest computer for doing scientific computing. And that computer is called Frontier. It has a footprint of about 2 tennis courts. So think about a room full of cabinets connected together, intended to be used to solve one problem. That's the purpose of this machine, to solve some of the most challenging problems that we have. The Department of Energy runs that computer, and that computer is used for open science, not classified work. We have other labs that do classified work. This is used for open science work. There were other supercomputers. China has a number of supercomputers as well, and I'll talk more about the Chinese capabilities and what's happening on that score. But this is the way our machines are typically built today. Back in 1993, well, actually it goes back further. Back in 1978, I was part of a software project called LINPACK, and as part of that project, I put together a benchmark. That benchmark measured the performance of a computer solving a very standard mathematical problem, a system of linear equations, AX equals B. And it solved that problem using the technique that I learned back in high school, Gaussian elimination with partial pivoting. So a very simple method implemented using the LINPACK software, and I measured the performance of a computer based on solving that problem. So we're looking at performance. So I'm talking about operations per second, and I'm talking about floating point operations, or more specifically 64-bit floating point operations. An operation in this context is an add or a multiplication. So we're looking at flops, floating point operations per second, and that's what the benchmark is trying to register. So my colleague Hans Moyer, who worked at the University of Mannheim, had a list of the 500 fastest computers in the world. They were ranked by theoretical peak performance. Theoretical peak is the paper and pencil calculation for what the manufacturer claims for their computer. I had a benchmark that actually measured something, and Hans suggested that we get together and put together a list, and we wanted to call that list the Top 500. So the Top 500 has been going on since 1993 and measures the performance of high-performance computers solving that problem, solving a matrix problem, AX equal B, using that algorithm, Gaussian elimination with partial pivoting. So we have data that goes back to 1993 for solving that problem. That list comes out twice a year. It comes out in November as well as in June, and it reflects the state of high-performance computing. The way this works is if you had a high-performance computer, you would download the benchmark, you can optimize certain components of it, you would run the benchmark on your machine and send the results to us. We, of course, check to see that you got the right answer in terms of 64-bit accuracy, and then we would register your machine as having a certain execution rate, flops, for your machine. So that's the benchmark, and that's the way it's carried out. So I want to talk about the top 500 list. There's a lot of interesting things that come out of it. So back when we started in 1993, there were 65 systems that used Intel instruction set. And in fact, it was the Intel i860 architecture. And this graph here is, let's see, can we see that dot? Oh, there it is. So this graph is reflecting the number of machines that used Intel processors. So it goes to 500, and you see there was a modest number of machines that used Intel parts. Most of the machines on the list back then had supercomputers that came from Hitachi, NEC, Fujitsu, Thinking Machines, SGI, Cray, and IBM. So they were the manufacturers of high-performance computers. And many of those companies made their own processors. So they invested, they developed an architecture, and they put together an architecture based on that characterization. Something happened back in the turn of the century. So it was the attack of the killer micros. So the Intel processor, the x86 processor, the instruction set, and that processor was capable of doing and competing with many of the manufacturers that were making supercomputers. So as we see going forward from this period, Intel processors and the x86 architecture, including AMD, have really dominated high-performance computing. So high-performance computing is really based on commodity processors leveraging that instruction set that Intel has. And those companies that made specialized processors couldn't maintain the business, and they went out of business or went out of the high-performance computing business. They couldn't sustain the machines at the cost, given that these commodity processors were much cheaper and provided a capability which was very similar to what we had with those high-performance computers. So today, 95% of the high-performance computers on the top 500 list are based on the x86 architecture. I find that stunning. A commodity processor driving high-performance computing that way. If we take a look at the frequency of the processors on the top 500 over time, we get something that looks like this. So I'm looking at the average frequency of the processor on the top 500 list. So we see that it was rising until roughly 2004. So it was about 3 gigahertz around 2004. And then something happened. Donard scaling ended. So Donard scaling is this incredible situation. We always think about Moore's law, but the real secret sauce in some sense is Donard scaling. So Donard scaling, Robert Donard is a scientist at IBM Watson Research, and he had a paper which said, as the dimension of the devices goes down, the power consumption will also reduce. So we can put smaller transistors that run faster on the chip that are using less power and cost less. This was an incredible situation that took place. Unfortunately, as the size or feature size of the transistors got smaller, there were some problems. And what happened was there was voltage leakage, and the result of that voltage leakage caused the chips to heat up. So they couldn't maintain the continuation of the reduction in the increase in the frequency of the processors. It would cause the chips to heat up too much. So we're stuck at basically 3 gigahertz for our processors. And the reason goes something like this. The power consumption is proportional to the voltage squared times the frequency. So think about, and the frequency is roughly proportional to the voltage for modern processors. So the power looks something like the frequency cubed. So if you double the frequency, make something run twice as fast, the power requirements for that chip go up by a factor of 8. So that's too much to maintain. We can't continue that rise that we saw in the early days with Donard scaling. So that's one reason why we're capped at 3 gigahertz roughly for our processor performance. So I mentioned that our processors or our high-performance computing systems are based on commodity parts. 95% are based on the x86 instruction set. We use commodity accelerators as well to boost the performance. And NVIDIA is an example of those commodity processors. So of the supercomputers that have accelerators, 96% use NVIDIA accelerators. The other accelerators on the market come from Intel and AMD. So they also make accelerators that can be put together. The computer that we have at Oak Ridge is based on AMD parts. So they use AMD processor together with AMD accelerators, again, to boost the performance. We see that commodity interconnects are also on these systems. So 85% of the top 500 systems use gigabit Ethernet or InfiniBand as the interconnect mechanism, not special purpose things that allow for much greater bandwidth and lower latency. They're using commodity parts. And this is really to lowball the price of these machines. So the way it usually works is if you're going to go out and buy a supercomputer, you have a performance target in mind. You want the supercomputer to be at this level, and you have a certain amount of money to spend. And now you ask for bids from vendors. And the vendors go off and cobble together a machine with those commodity parts, trying to get the price as low as possible, trying to make that performance point that you're asking for. And the result is a system that looks like this, based on commodity parts. And then they throw it over the fence. And now the scientists are left scrambling, trying to figure out how to use a machine that's based on these commodity parts, which have very, I'll call it, unbalanced performance characteristics, as we'll see. And of course, 100% of the systems are based on Linux operating systems. Not a surprise, really. That's unlike the hyperscalers. So the cloud vendors are doing something quite different. They're not building their machines based on commodity parts. They're going out and they're designing their own processors. So the vendors like Google, like Amazon, like Facebook, are designing their own processors to meet the needs of their cloud-based services. And they have tremendous resources that they could put together, financial resources, to invest in hardware, invest in the design of the hardware, taping out and putting together processors that are targeted for their audience. That's quite different than what we do in the scientific community, where we don't have that unlimited set of financial resources to invest in high-performance computers. If we take a look at the number of conventional machines or vendors that produce equipment that fits into the high-performance computing space, and we look at the capital, the market capitalization, the net worth of these companies, we end up with the traditional companies like HP, Intel, IBM, and AMD. You know, if you add up all of the market capitalization of these companies, we get to about $2.6 trillion. And on the other side, the hyperscalers, we see this incredible situation where their capital worth is just dominating what we see from those conventional computer users. So even the Chinese participate in this with Baidu, Alibaba, and Tencent. They have companies that are producing these things. They also are making their own processors to use in their services. So just an incredible situation. The one outlier here is NVIDIA. So NVIDIA's capital worth today, you know, is something which dominates and sort of rivals Microsoft and Apple. You know, they're greater than Meta, they're greater than Amazon, they're greater than Google. That's a stunning achievement, and that's being driven, of course, by artificial intelligence, AI, machine learning, that need the kind of processors that NVIDIA has and driving that market. So this is what our environment for scientific computing looks like today. It's highly parallel. It uses distributed memory. The programming model is MPI, the message passing interface, together with something called OpenMP for programming on a node. So we have nodes and we have multiple nodes connected together. Connecting things together require us to pass messages, and we do that through MPI. We program in C, C++, even Fortran is used on these machines. The machine at Oak Ridge National Lab is the fastest machine. That machine has a theoretical peak performance of 2 exaflops. 2 times 10 to the 18 floating point operations per second. That's an incredibly large number. I have a hard time getting my hands around that number. So think about if everybody in the world did 1 operation per second, everybody in the world, it would take 4 years to achieve 1 exaflop of the world's population doing 1 operation per second, just to put that in perspective. And this machine does 2 exaflops per second. So this is a tremendous amount of computational power. It has 8.8 million cores. So if you're going to program this machine at scale, you have to coordinate, orchestrate that number of processes on your application in order to have it run efficiently. And this machine is based on an AMD CPU multi-core, plus 4 AMD GPUs. So that's the node that's on the machine, and that node gets replicated 9,400 times to fill out those cabinets that run on that machine. But the important thing to note here is that 98% of the performance is coming from the GPUs. So the way these GPUs work is the CPU's in charge. It sends some data over to the GPU and tells the GPU to do some operation on the data. And when it's finished, you can collect the answer back and send it to the CPU. So there's this constant play between the CPU and GPU. The GPU is really the thing that's powering that peak performance, and 98% of the performance is coming from that GPU. So if you don't use the GPUs, you should really forget about using this machine, because you're only going to get 2% of that exascale performance, potential performance. So our machines are heterogeneous. They have CPUs and GPUs. That's going to change in the near future, where there's going to be a fusion between the CPU and GPU that's happening today with processors that are emerging from companies. Communication, though, is something that's very expensive. So I talked about floating point operations. In the old days, floating point operations were very expensive. Adds and multiplies were very expensive. Today, it's communication. Passing information around from various parts of the machine, from memory to the CPU, from distant memories on distant nodes of the machine. Passing information is the most expensive thing that we do on our high-performance computers today. And in some sense, our computers are over-provisioned for floating point arithmetic. We can't possibly use the potential that's there because of the communication cost associated with it. And there's this conventional wisdom that said if you have 2 algorithms, one algorithm does fewer operations, you want to choose the one that has fewer operations because it's going to run faster. But today that's not the case because of communication costs. So communication really has to be taken into account when we look at a comparison of algorithms. And floating point computations today can be dialed in at various levels. Traditionally, we think about 64-bit floating point operations and 32-bit. That's the way science has been done. Scientific computations have been done for many years. And today, we have 16-bit floating point operations. There's hardware that has 8-bit floating point operations, and even 4-bit floating point operations. Those lower levels are there not for the scientific guys, but for the AI application. So machine learning doesn't need high precision in their computations. They can get by with much shorter length of precision with it. And the hardware is there, of course, to meet that demand because of the increase in need for those kind of processors. So we see processors today that have even 4-bit and even 2-bit operations going on because of the cost associated with it. This is a chart that gives you a sense of how supercomputing has evolved over the last 31 years. So what we're looking at here is time on the x-axis and performance on the y-axis. It's on a log scale. The red is charting the #1 machine, the fastest computer. So the fastest computer today is the machine at Oak Ridge National Lab, and it's sitting here at 1.2 exaflops. The guy at the bottom of the list, just made it on the list, is 2 petaflops. So exa to peta, there's 3 orders of magnitude difference. This guy here is 1.2 times 10 to the 18. This guy here is 2.3 times 10 to the 15 operations per second. And that's running the benchmark. So running that problem, AX equals B, using a dense matrix computation is what's being reflected here. So there's a lot of interesting things that you can make out from this graph. We see this inflection point here. If you take a look at the trend lines, you know, what's going on there? What happened there? Well, I think it's a combination of things. There's Moore's law slowing down. There's the Nard scaling ending. There was a financial crisis that took place, slowing down the purchasing of high-performance computers. So I think a number of things contributed to that. But again, tremendous advances in really a short period of time. Back in 1993, the #1 computer was at Los Alamos National Laboratory. It was used for nuclear weapons simulation. And that computer ran at 60 gigaflops, 60 billion operations per second. My laptop, this machine here that I'm using to give this talk, I can run the benchmark on. And I get 426 gigaflops. That's stunning. This is a computer I use mainly to read email. And you know, I get a performance that outperforms the machine used at Los Alamos National Laboratory, which had 1,000 processors, which was used to do nuclear weapon simulation. Just incredible changes over a short period of time. And you know, my laptop would have been on the top 500 list. It would have been #1 back in that into perspective in terms of how the changes have evolved over a short period of time. All right, this is the list of the top 10 machines today. And the way to read this is the #1 machine is at the Department of Energy, Oak Ridge National Laboratory. That's a open science laboratory. So the Department of Energy has two kinds of laboratories, open science and defense related. So NNSA is the defense side. Los Alamos, Livermore, and Sandia do weapons research, classified work. Oak Ridge, Argonne, and Lawrence Berkeley Lab are the open science laboratories. All have high-performance computers. We have the fastest one. Again, it's based on AMD parts. It's put together by HPE. HPE does not make processors. They're an integrator. They take stuff and put it together, and then we buy it from HPE. And our machine has 8.6 million cores in it, and it achieved a performance of 1.2 exaflops, 1.2 times 10 to the 18 floating point operations. And that was 70% of the theoretical peak. So the theoretical peak is a paper and pencil calculation. How many cores do you have? How many operations can you do per second? Multiply all the stuff together, and that gives you a problem on your machine, and you get something much less. And they got 70% of their theoretical peak performance. The machine uses 22.7 megawatts. So what's a megawatt? So here in East Tennessee, at my home, if I use 1 megawatt for a year, I'm going to get a bill from the electric company, and that bill will be for $1 million. So a megawatt year is $1 million. So this machine, to turn it on, is about $22 million just to run the machine, the power needed for that machine. That machine costs $600 million. So that's a small part of the overall cost of the machine. And you can see some of the other machines down the list here. I've highlighted the machines that use accelerators. So in this column that says computer, there's in red are the machines that use accelerators. Of the top 10 machines, 9 machines use accelerators. The only one that doesn't is this machine here in Japan. It's the Fugaku system. It's an ARM processor, and they've modified the ARM processor to have vector instructions. So this machine, in some sense, gets its performance by executing these vector instructions on their machine. And you could just scroll down the list here and see the percent of peak performance, 70%, 51% of peak performance for a machine at Argonne National Laboratory. In fairness, this machine is just coming up. It's a new machine that was just put on the floor, and they're still sort of shaking it down. But look at the power consumption, 38 megawatts of power in this machine, so it's a very hot machine. Some of the other machines you could see, the US has 5 machines on the list, Japan 1, Finland, Switzerland, Italy, and Spain round out the list. There are two machines that are provided by cloud vendors. One's Microsoft at position number 3, and at position number 10, the machine at NVIDIA is also used for cloud-based services. So they put together a machine, ran the benchmark on their cloud, and submitted it to us. This is a list. There are 500 dots on this list here. So the x-axis is listing position number 1 through 500, and the y-axis is giving us the speed of the machines. So you see the list is very, let's call it top-heavy, a hockey stick effect. We have a lot of machines at the lower end, and just a few machines giving us this very high performance. So if I was doing this list again, I probably wouldn't have 500. I may have 50 machines, because that really reflects what's being the top machines in terms of scientific computing. Okay, this is the machine at Oak Ridge National Lab. The peak performance of 2 exaflops, 20 megawatts of power. It's based on an AMD processor plus 4 AMD accelerators, and then it's built out using 9,408 nodes. The interesting thing is if you use 16-bit arithmetic, the short precision that's there for machine learning, the peak performance is potentially 11 exaflops. So using short precision allows the machine to run a lot faster, and you could exploit that if you have applications, scientific applications, that can use it, or if you're doing some machine learning training, you could also use it for that purpose. But again, 99% of the performance is coming from the GPUs, so you better be using the GPUs on this machine, or you get very little performance overall. And again, 8.8 million cores is what we see on this machine. So again, this is the chart of the number 1 machine on the top 500. It's interesting to see the effects. So we reached a teraflop. So a teraflop is 10 to the 12 operations per second, and that was back in 1997 at a machine at Sandia National Lab in Albuquerque. It was called the Sandia Red Machine. 11 years later, we reached 3 orders of magnitude greater in terms of performance, and that was a machine at Los Alamos National Lab called Roadrunner. It used the IBM Cell processor, which was used in the Sony PlayStation. So that was the real driving force for performance on that machine. And then about 14 years later, we saw the first exascale machine, 3 orders of magnitude in 14 years. So it's taking longer to get to higher levels of performance. And a question is, when do we get to the next big threshold? Zetascale computing, which would be 3 orders of magnitude greater. And the projection is it's not going to be 10 years. It's going to take a lot longer to get to that point. We can't even make the projections at this point. China is rumored to have 4 exascale machines, but they haven't submitted the results to the top 500. They've been very quiet. Back in 2022, they had the most supercomputers. So this chart here is listing the number of supercomputers on the top 500 list. So China here has, I can't quite read that number, so it has 162, and the US has 125 machines on the list. So you see the difference. So China has invested in high performance computing. In 2001, China had 0 supercomputers on the list. So they made a tremendous investment to build up high performance computing within the country. More recently, China has stopped sending results for the top 500. So the US now has become more dominant. As machines fall off the list, the US is populating more machines on the list, and China has refused to send new entries into the list. So why have they done that? Well, the US has taken action against China in terms of limiting technology, and my guess is China doesn't want to have more restrictions applied to the acquisition of parts that they might use for high performance computing, or devices that they may use for making processors. So they've stopped submitting numbers to the top 500 list. But we know that there are 4 large machines in China that are being used to do their effective high performance computing workloads. One of those machines is specific for AI, machine learning technology. So we've had this benchmark for a long time, this thing called the LINPACK benchmark. And it's been around since 1979, and a lot of positive features have come out of the benchmark. It shows trends. We get to understand how these machines perform on a certain problem. The problem has been fixed over time. We have the same kind of matrix. We require a certain kind of accuracy out of it. But a lot has changed since 1979. Arithmetic back in 1979 was very expensive, and today it's been over-provisioned. The expensive part is communication today, and this benchmark really doesn't take into account the communication. It highlights floating point arithmetic. And if I could put that in perspective, this algorithm does n cubed things with floating point arithmetic and only n squared data movement. So we get this bulk of the computational time being done with floating point arithmetic. So the LINPACK benchmark is no longer strongly correlated to what I'll say we do on our high-performance computers. Maybe it was back in the 70s, today it is not. And maybe we need something that better reflects what we do on our high-performance computers. And if you design a machine for a good LINPACK number, you're probably going to be imbalanced. You're probably not going to do very well on the standard applications that are run. So today's high-performance machines are used to do modeling. That modeling involves a partial differential equation. It's a three-dimensional partial differential equation. When you do the discretization of that differential equation, you end up with a system of linear equations again. That system of linear equations, however, is not the same. So the kinds of applications I'm talking about are climate, nuclear reactors, fusion, supernova calculations, material design, digital twins, and so on. All of those computations involve a three-dimensional partial differential equation, which we discretize, and we get a system of linear equations. So we have a benchmark that tries to imitate that, and this benchmark is called HPCG. It uses an algorithm called the conjugate gradients algorithm. The previous benchmark, the LINPACK benchmark, was a direct algorithm. You went through some number of steps, n steps, and you got a solution. No issue about that. That was the way it worked. This algorithm is iterative. So you iterate until you converge to a solution. The matrix looks something like this. So it's a large sparse matrix. It has this structure associated with it. These diagonals are full. The rest of the matrix is zero. And you do an iteration on it. The thing that we try to model is this 27-point stencil that is the discretization that we're following with the partial differential equation. We allow a preconditioner to be used in this partial differential equation to speed up the computation. And this is the results for this benchmark on the high-performance computers. I'm just listing the top 10. So the way to look at this is the winner in this case is this machine from Japan. It's called the Fugaku system. It's at Riken in Kobe, and it's based on that ARM processor that I mentioned. This column here is representing what we got using the LINPACK benchmark, the old benchmark, the one that did a system of linear equations using Gauss elimination with partial pivoting, the one that was very computationally intense. The new benchmark is HPCG, and it's not computationally intense. It has a lot of data movement. It does some computation, but the bulk of the time is going to be passing information around in order to do that iteration pattern. And the result of that is we see that we end up with the percent of peak performance being much less. With the LINPACK benchmark, we were seeing numbers like 70% of peak performance. Here we're seeing the best number at 3% of the theoretical peak performance. And some machines are getting 1% or less. So 1% or less, that's almost a shocking thing. So think about a race car, and think about a race car that goes 200 miles an hour. And driving gets only 1 mile, 2 miles per hour. You would be a little bit disappointed with the performance of that race car. But that's what's happening with many of the applications that are actually run on these high-performance machines. Very low return from the potential of these machines, and basically because of communication. Basically because the machines were not designed to do the kind of workload that's needed for scientific computing. We have an imbalance between the processor and the communication network. The communication network doesn't have the appropriate bandwidth or latency to match the needs of the applications that are done there. So it's really all about data movement. And we really need to think about building machines that can effectively move data through the system much better and have greater responsibility for that. So today, machine learning and AI have taken off. And there's a lot of research that's been done on these algorithms. So why has it been so, why has it just now become so important? There's a number of reasons. Well, today we have a flood of data that can be used for training. The whole internet can be used for training these neural networks. We have increased computational power, mainly coming from the GPUs of the machines. So we can do the kinds of computations that are needed much more rapidly than we could before. And we have better algorithms in theory based on machine learning that all sort of help in driving this to the place where it is today. And we have this increased support coming from industry. So we have this ecosystem that really supports our AI capabilities today. These are the companies that are involved in developing some aspect of that ecosystem, from hardware to software to specialized devices that are being put in place to help drive machine learning and computational science. But with machine learning, it's really about linear algebra. Again, it centers on small matrix computations. So looking at small, relatively small, 3 by 3, 5 by 5 matrix multiplications, dense matrix multiplications. And those GPUs do a great job, and they can get by with short precision in doing that. So today, our systems that we use, things like ChatGPT, are built in the following way. We have a model. That model may have 2 trillion parameters. We basically take all of the internet, scrape everything from the internet, take all the images that we have and do OCR on them to take the information and pour them into this training. And the training produces a model. That training is very expensive. It costs between $10 and $200 million to do the training. So think about ChatGPT or Gemini from Google. It cost about that much money to do the training for ChatGPT 4 to get it to the point where we can use it. So that's just the training part, and that's what we call a pre-trained model. So we take that pre-trained model, and now we help it along. Oh, this is the indicator here, which says what it costs for various models. So what I have here is different models, and looking at the cost in terms of dollars that it costs to train the model itself, and looking at the number of parameters that are in those models. And again, we have these things, $100 million just for the training of some of these models, an incredible expense. So we take the pre-trained model and we help it along. So basically the pre-trained model is based on all of the internet, and you have something which has the education maybe of an undergraduate, and now we're going to help it along. We're going to push it in the right direction. We're going to make it so it works for certain areas, maybe looking at specialized data to help push it along. So we go and we fine-tune that model with some human input. So human input is there to push along questions and push along answers into the model so it gets things correct. So that turns out to be a less expensive thing, but it's time consuming. So that part of the process takes around $100 million to $1 million, $100,000 to $1 million worth of GPU time to get to that point. And then finally we have a model which can be used and satisfy your queries. So now we have a model that is like ChatGPT, where we can ask questions and get responses and carry on a dialogue that we can. And that's very quick. So that part of the operation doesn't cost very much. We've paid for the training on the upstream, and now we can get the benefits of it. Okay, so let me conclude here. I think I've used up my 45 minutes. The software, I'll say, always follows hardware in terms of development. Every decade or so, we have to redo the hardware, redo the software to match the hardware. And the hardware is put together with commodity parts in terms of scientific computing. And that leads basically to an imbalanced system. We don't have the resources in the scientific area to build our own hardware to match the needs of the applications like the hyperscalers do. So we have this ability to use short precision today. So in the scientific area, there's a lot of work going on trying to exploit that hardware that has increased capability, trying to understand if we can use 16-bit arithmetic to solve our problems, or get away with 8-bit floating point arithmetic. And those are research questions that have to be investigated. We want to ensure the integrity and make sure we get the right answers, but we want to see if we can exploit that. And again, I mentioned the old adage of things taking, of looking at the operation count and using that to project the time to solution. That's no longer true because of the communication layer, and we should be thinking about algorithms that go beyond the box, outside of the box. Look at algorithms that are what I call recklessly responsible, that try to do things which are potentially going to get into trouble, but we can detect when they do get into trouble and then back off and do something if they did get in trouble. But if they don't get in trouble, they can get to a solution very, very rapidly. So I'll end here, and I'd be happy to answer any questions that you might have. Thanks for your attention.
Do you have any comment on why the optimization of the computing capabilities are so mismatched to like the HPGL?
Sure. So the mismatch is occurring. It's very obvious. You know, we have, when we buy a computer, again, we have a certain amount of money in the scientific area. I have $600 million, and I need this performance level. I need a performance level of 2 exaflops. So the vendors go off and put together a bid with that in mind, and they bid things, they want to make it as low cost as possible. So they use the commodity parts. They use commodity processors and interconnects, and those two things are mismatched. The processors are very fast. Communication can't keep up with the processor speed, and the result is there's nowhere where it's very difficult to get at the theoretical peak performance. So it's that mismatch. If we had infinite resources, we would do something called co-design. Co-design says we're going to get the architects together in a room with the application people and the software designers, and we're going to design a machine based on the needs of the applications. Everything is about the science. We're trying to drive science forward. That's why we buy these machines, and we should be looking at what the science needs in terms of getting the job done. So we don't have an unlimited set of resources, so we're stuck in some sense with this mismatch that occurs, where our friends over at the hyperscalers, they can invest and develop architectures which match the needs specifically for their problem and get a much better return. So it's a financial situation, basically. If we had more money, we would do it right. We don't have the money, so we get what we pay for in the sense of a mismatch.
Hey, first of all, thanks for the talk. It was really fascinating. So you were talking about how the HPC world use commodity stuff and the cloud vendors use their own custom hardware. Where do you think that's going to go? Like, will the cloud vendors eventually, like in some future, also use commodity, or will their solutions become the new commodity, or what's the convergence point for that?
Right. So let me just point out that you cannot buy processors from Google. You cannot buy processors from Meta or from Amazon. They don't sell their processors, they sell the services. So you can't go out and acquire what they have and put it in place. You could just buy their services. So why don't we do that? Well, if we do a cost analysis, it's at least a factor of 2 greater to buy cloud services than to use our own computers. That's the rationale that people have put together for that. So we're going to buy our own machines. So where's this driving the industry? So you could see that NVIDIA has this incredible demand for their parts today. And that's being leveraged by machine learning. Machine learning doesn't need large accuracy. So NVIDIA is putting in place small, short precision, very short precision to meet the needs of machine learning. My concern is that NVIDIA will throw away the ability to do 64-bit floating point operations or 32-bit because it's not needed for machine learning, and that's where their bread and butter is. So they may abandon, I'll say, what we do in scientific computing, and that would be a mistake. Or they may have a SKU, they may have a version of it, but it's going to be very expensive to get that SKU. So that's a concern that I have in terms of how the industry is going, and I don't know what can be really done to prevent that, but research is needed in terms of trying to exploit the precision that we do have.
Thanks, great talk. Just one question. Have supercomputers ever been hacked?
Hacked? Oh gosh, of course. Yes, of course they've been hacked. Yeah, so it's like any other computer. There's protections in place, and if you're doing classified work, there's an air gap between the computer and the outside world, and things are confined in that machine. But computers can be hacked, and many accounts are on machines, and those accounts could be fall into the wrong hands, let's say, and people could use those computers for doing things they shouldn't be used for. But they have some checks on that, and they could spot it, I hope. And yeah, so hopefully people aren't to do Bitcoin or something else like that. Yeah.
Dr. Dongarra, this is an absolutely fantastic talk. My name is Adam Thompson. I'm with NVIDIA. And I think one of the interesting things about this community is we're dealing with essentially edge-based sensors which vary in size, weight, and power. So sometimes you're dealing with like massive radars or big phased arrays like radio telescopes. And so as we're trying to put this real-time, high bandwidth, low latency data and have integration with something like a supercomputer for a digital twin or simulation or just crunching numbers, how do you view that the modern supercomputer needs to change to keep up with this deluge of data that has real-time requirements coming from the edge?
Right, so edge computing is an important aspect to how we do business today. We think of a lot of data coming from the edge, and we need some way to filter that data. So we need processing that will allow us to reduce the volume of data and then push that data upstream from the edge to the computer. We intermediate computers along the way where we do processing on the data and again trying to reduce or filter the information before we push it upstream to the supercomputer and do the final crunch. But yes, edge computing is an important aspect. It's another one of these important changes, revolutions that have taken place and will have and continue to have tremendous impact on computing and how we use the total ecosystem that we have to get us to a better solution.
Hi, thank you for the presentation. Of all the supercomputers you listed, almost the majority of them were like x86, based. Except for the one I believe Japanese machine. Do you see ARM architectures being pursued in the future to any degree, either for power or efficiency's sake?
Okay, so ARM. So what do we have to choose from? We have x86 architecture. We have ARM. We have RISC-V architecture. We have perhaps some others. The Chinese, by the way, in their supercomputers, they have totally different. They design their own stuff. They were forced into it, so they're not using Western technology. They're building their own technology, which is quite different. So, those are potentials. ARM, the way it's being used for high-performance computing is not low-powered. So don't think of cell phone ARM. Think of an ARM processor which has a lot of power associated, a lot of the ability to solve more challenging problems, and is being used for that. So the Japanese machine, while it uses ARM, is very it's in the mix with the others in terms of the power consumption. So you're not getting any real benefit from the stuff we have on our hip. We're getting the benefit because it's a different architecture. We could then modify it easily, and in the case of the Japanese, they put a vector extensions in it, which gives them a boost in terms of performance. But having said that, there's only a few machines today which use ARM processors, a handful or two handsful of machines on the top 500 list. There are no RISC-V machines on the list. I would expect that to change in the future, but that's the world that we live in today, where it has a dominance from Intel's x86 instruction set. AMD and Intel share that and produce machines in that space.
So looking at programming for these devices, it feels like it's getting more complicated, and I as a developer have to understand more of the CPU architecture, the GPU architecture, the data buses, the memory architecture, and it feels like maybe software isn't and the tooling isn't keeping up with the hardware. So I was curious on your take on that and where you see that going.
Right, so I'm a software guy, so I'll say that we always have to follow the hardware, and that leads to many problems. My image of this is every 5 years a new supercomputer gets thrown over the fence, and the application people and the software developers scramble for the next 4 years trying to figure out how to use that machine, and after a 4-year period we do a pretty good job of doing matching the applications, and then another machine gets thrown over the fence, and we have to start that process over again. So we're constantly in a mode where we're redoing things to match what we see in terms of the hardware that we have. We don't have that co-design. So if we had a situation where we can get the architect together with the application people and the software designers, we might be in a better position to design a machine that fits the needs of the applications more tightly. But unfortunately, we don't have that at our disposal. And hardware design is expensive, so it's not a surprise that we don't have that. I like to think in the old days, we had a lot of research projects at universities that developed hardware that allowed one to have experiments. I can remember back at Illinois having the Iliac 4, or at CMU having an experimental machine, or at New York at the Courant Institute having the Ultra computer. So there were a number of these experimental machines that were paid for out of research, and we don't see that level of machine development today. Of course, there's architecture research going on, but not at the level of building a machine that's intended to experiment with an architecture that's really new. So the hardware, and we need to figure out some way of matching that. Think about 8 million cores. How are you going to program that? You can't have simple loop level programming for 8 million cores. A fork and join doesn't work in that environment. You're going to spend all your time waiting for that synchronization to occur before you carry on the computation. So we need different models that can accommodate the levels of parallelism that we have, and different ways of, our trick in computer science is to encapsulate things so we can use those encapsulated versions in our applications.